Hi class, this week we have one lab and it is second part to thermochemistry. So this is going to be lab 12, enthalpy of combustion for fuels. A calorimeter, last week we used a calorimeter, this time it's going to be a different type of calorimeter with different conditions. A calorimeter is used to determine the heat associated with a chemical reaction, whether it gives it off or whether it absorbs it. We can measure the surroundings out of it. Last week we used a constant pressure calorimetry. So the coffee cup was constant pressure because even though it was closed, it was still open to the environment. So the pressure was the same as the atmospheric pressure. This lab, we are dealing with an very well insulated container, and the volume is constant. So it's different in the sense that no heat or mass leaves this container and it is not open to the environment. So no work is being done also. There is no change in the volume, and I'll come back to that in a little bit. So the energy change is measured by the temp difference of the water and the other calorimeter parts, which we did not account for last week. We did not calibrate the coffee cup, which does actually absorb some of the heat from the reaction of the metal being transferred to the water. Constant value calorimetry, this is carried out in a bomb calorimeter. It sounds probably scary. It really is not. I did it as a grad student. It's just this big, huge steel. In my case, the professor said it was over 50 years old. You take a very, very, very small amount. I mean, you still have to be careful with this stuff, but you take a small amount and it conducts a combustion reaction in this contained calorimeter. So it's designed to withstand high temperatures, and it's designed to also handle high pressures. So it has to be sealed and insulated, and this thing was very heavy. We had to seal the top by screwing this top on. It was interesting. Bomb calorimeters are as close to a true isolated system. So unlike last week where the enthalpy was equal to Q, which was the heat flow because it was at constant pressure, we are now looking at internal energy. None of this really is involved in this lab. They're not going to ask you, at least as far as I can tell, any of this, but I just want to briefly bring it up. We're looking at internal energy of this. So Q stands for heat, W represents P versus pressure versus the difference in volume, but because there's no difference in volume, this is zero. So long story short, it's still equal to Q, which is enthalpy. I know, like I said, some of this may not make sense. This is actually in your reading, and it talks about this and under the internal energy, which in some books is known as E, and your book is used as U. So lab flow is going to refer to enthalpy, so we're just going to refer to that. But in some cases, you should know that when you're dealing with constant value, it's actually the internal energy. It's not straight enthalpy because it's at constant volume and not constant pressure. Bomb calorimetry. It's a reaction that's carried out in a sealed container. The heat is absorbed or released, and using a certain amount of water and the temperature, we can determine what's going on in this reaction. You need to understand system and surroundings, especially when it comes to thermochemistry, because this stuff can get really confusing. So you have to know what definitely is the system, what definitely is the surroundings. In this case, the system is the chemical reaction, and the surroundings is the solution, the calorimeter, the bomb calorimeter. It's everything that's not the surroundings, so the water and the bomb calorimeter. If an exothermic reaction occurs, you see Q with the arrows going out, you can see the temperature increases. And then if it's an endothermic process where a reaction pulls energy away from the water and the calorimeter, the temperature will decrease. Heat capacity, it's standard to use the total heat capacity of the calorimeter and the components plus the water inside. So we're accounting for everything that, since it's insulated, we're accounting for everything that's in the surroundings, which is the water and the calorimeter and anything that's also involved inside that calorimeter. We always calibrate. Again, we didn't calibrate for last week's. This time we always calibrate. We calibrate the calorimeter before we do our reactions. And this is where things get really confusing for students. The best thing I can tell you is understand the equations that I'm going to give you and understand the units that go with them. Because if you get lost or stuck on something, look at the units. The units will help guide you into what you need to solve for. So this is heat capacity. We are looking at the heat capacity. Basically, we're going to calibrate the calorimeter. And it is in 2 units. It's in joules over Celsius or joules over Kelvin. And I'll show you the exact, this is the exact equation. However, it's missing a negative sign here, and it'll be on the next page so you see it. It is, so here it is, the product of the calorimeter and the change in temperature for the chemical reaction that is used with a known substance and a known amount of volume of water. They can use this heat capacity and plug it into the second part with the actual experiment. So this is this, think of this as a step as setting it up. So the heat flow of the solution calorimeter, which is opposite in sign of the heat flow of the reaction. What does that mean? Well, you can see it right here. So it's opposite of the heat flow of the reaction, and this is what we're plugging in. Make sure you keep negative signs and keep them throughout. If your answer has a negative sign, you will be marked wrong if you do not use it. So don't be hesitant to carry out. You got to show that these are exothermic reactions or endothermic reactions. And if you leave it off, it's going to think it's endo when it's really exo. So you may get the value right, but if you leave something off like that, it's going to be wrong. Trust me, I know this. It happened to me. A bomb calorimeter needs to be calibrated before it can be used with your sample. You use 1.325 grams of fuel. The enthalpy of combustion, I'm just going to call this QG. You should definitely read your PDF very thoroughly because this is a complicated lab. And I'm not going to keep saying enthalpy of combustion, and there's also another fancy term for it in the other one. So QG is negative 52.5 kilojoules per gram. This G here, let it remind you that this is for grams. This is in gram form, kilojoules per 1 gram. If the water temp in a calorimeter increases by 12 degrees Celsius due to the reaction, what is the heat capacity? So this tells you that the water increased. So this has got to be an exothermic reaction. The water was given energy. First thing you need to do, understand what it's asking for. And you can learn this by learning what the units are. So this is asking for, what is the heat capacity of the calorimeter? So this is going to be the heat capacity of the calorimeter. Well, you have the delta T. It's right here. You do not have the heat capacity of the calorimeter, which is right here, but you have the reaction. The reaction is right here. So you can take some of, oh, sorry, no, it's not. It's this one right here. You can take some of the information that's given to you. So you don't have this and you don't have this, but you're given enough information from other things that you can use. Here is the Q reaction. Make sure you understand Q reaction. Q reaction is 1 unit. It's kilojoules. It's very similar to what we did last week when we had to solve for specific heat. Q was on top. It was the heat flow. That was the Q. This is the same thing. It's kilojoules, and that's what we're going to use. So we set up this equation, and all these equations are in the PDF. So I really strongly suggest you read these very thoroughly. And we have our QG. So we set that up here with the negative sign, and then the mass that's burned. The mass that's burned, the grams are going to cancel out. That's going to give you your heat of flow reaction. And it's negative, it's exothermic. We see that. And now we're going to take this and plug it in here. So once you solve, you isolate the C calorimeter, which is the heat capacity. You keep the negative sign, and the negative sign will cancel these two out, and it will give you a heat capacity of the calorimeter, and it should be positive, at 5.80 kilojoules per Celsius. So Q reaction has 1 unit, kilojoules. Heat capacity of the calorimeter, right here, has 2 units, kilojoules per Celsius. And enthalpy of combustion is, fancy naming QG, is in grams as the bottom. So kilojoules over grams. This is an important page in your PDF. It tells you what everything is that I just went over, and the units. The units are very important here, and this will honestly help you if you're stuck. The units will tell you what you need to do the next step. This is part 2. This is what you're going to be doing. You're going to answer all of these for part 2, and you're going to answer one of these for part 1. Everything is always in 1 mole and 1 gram. And here's a nice little diagram that will tell you what to do with your next step if you get stuck. So again, I'm going to say it again. Make sure you read your PDF. There's a lot of pages to it, but this is a difficult lab. So the fancy word for it is gravimetric energy density. I call it QG. It is energy provided per 1 gram per 1 kilogram. So how they do this, you see this nice little scale here of energy density ranking of hydrocarbons. you want to, if you put gas in your car, you want to get the gas that's going to be most efficient, meaning you're going to pay a certain amount and you're going to expect to go a certain amount of miles. But what if you buy, let's say, I'm just going to throw something out there. What if you buy cheaper gas that you think is a good deal, but in the long run, you end up spending more because it's burning through faster. So now you're making 2 trips and buying gas twice, when if you had bought the better gas that was more efficient, you bought it once. And that's what this is. This is telling you a scale of that. So if you have 2 substances here, you have one that's negative 25.6 kilojoules per gram, and substance B is negative 35.9 kilojoules per gram. Don't get stuck on the negative. We know these are exothermic reactions. That's why they're there, but we're looking at the values themselves. So the negative and the positive are directions. It's a direction of what the heat flow, but we want the values. So in this case, we want the value that has the larger number, because that means it's going to, when it combusts, it's going to give out more energy, and your car can go further for longer. So substance B has a greater energy density than A, and that means B will burn less than A to produce the same amount of heat. So it's going to last longer. All right, so determine the energy density of a fuel sample. So here's another sample problem. You have a sample of fuel, was burned, combusted in a bomb calorimeter. The water temp increased, so this is exothermic, and the calorimeter I talk too fast, has a heat capacity of 5.43 kilojoules per Celsius, positive number. Determine the energy density of the fuel. So again, 2 steps. We need to get the heat, the heat flow, and then we're going to need to plug that in. So here we are given the reaction again with the negative sign. We are given the heat capacity of the calorimeter. We can plug that in here, keep the negative sign on the outside, and the change in temperature. And that gives us our reaction, our heat flow as negative 81.5. But we're not done. We're going to take this other reaction that's in your PDF, plug it in. So I take my negative and add it here. I take my mass that was given to me, and I know that my QG has to have 2 units of kilojoules per gram. That makes it easy to set this up, and it gives me my number with my negative. So I found this nice little GIF. It's not exactly matching ours, but it shows you a bomb calorimeter. First step, we calibrate it with using a certain amount of fuel and a certain amount of water and the temperature difference, and we do calculations, and it will give us our calibration of the calorimeter. Then we're going to take that value and we're going to use it for the second part, which is exactly what we're doing now. We're going to plug that in with the fuel that we're going to be assigned, the water amount, the temperature difference, and so forth, and we're going to do some calculations. So combustion reactions involve hydrocarbons. Hydrocarbons are all what organic chemistry is about. That just means C and H's, and sometimes oxygens as well. They do a different way of naming. Hexane. The hex stands for 6 carbons. Methane stands for 1. Propane stands for 3 carbons. Butane stands for 4 carbons. So they name by the amount of carbons in a reaction, in a compound. And the last portion of it, this ANE, that means it is a single bonded molecule. So that's when you hear hexane, it's 6 carbons. And we don't really worry about the hydrogens because this is single bonded. It'll all fill an octet and a duet on the outside. So that's all this means. It's a fancy organic names carbons instead of the way that we do when you first learn this. Here is a generic combustion reaction. Products are CO2 and water vapor. So now we're going to get into the lab portion. The first part, you are going to calibrate the calorimeter. And as far as I can tell, everybody's using hexane as the fuel. So we're all going to use the same fuel. You'll have different data points, of course, but everybody's going to use the same fuel. Then you're going to take that value of the calibrating the calorimeter, and you're going to plug it in, and you're going to determine heat flow, the QG, and delta H per mole. So kilojoules per mole, 1 mole. How much does it give the enthalpy off of this? Okay, so this again is from your PDF. It's a very important page. For some reason, LabFlow doesn't give you, when you do the lab, it tells you hexane, but it doesn't give you the value. The value is in your reading. So it's here, and this is actually a good page because you can see where they've worked out a problem, and you can see how they worked out the problem. So if you get confused on some of this stuff, This, I don't know what page this is, but this is in your PDF, and this is a good page to look at. I strongly suggest that you read this thoroughly before you do it. And I would suggest you do the lab, the data report, before you do the quiz. And it will make those problems on the quiz portion a lot easier. So the first part, we are standardization of burner with hexane. So I have included the hexane value here. These are my amounts and the equations I'm going to use. So the first thing I did is, if you can see, something was burned off. So my final is smaller than my initial, but we don't want a negative value. This is a process of elimination, is how we're weighing all of this out. We don't want a negative value mass. We want to know the mass that did combust, but we want it in a positive value. So when you enter this on LabFlow, enter it as a positive value. Don't put a negative number to this. The only negative numbers will be associated with the equations and keeping them everywhere they need to be. Okay, so then we have our temperature, and I add my temperature difference. So, okay, just checking something. First part, we need our heat flow. Remember, there is one unit, which is kilojoules. So I take my QG, which is my hexane. That's my hexane amount. The grams will cancel out. I now have my heat flow, and it's a negative number. I'm going to now calibrate my calorimeter. So I'm going to set this up. C, I'm going to solve for C using the equation, moving things around. And my negative and my negative will cancel out, and it will give you 9.48. You're going to do 2 trials of these. Make sure you use the trial. I have this in bold because this number is what I'm going to use on the second part, my calibration of the calorimeter. You're also going to need to do a percent error. The PDF gives you 2 examples, 2 different ways to do it. I'm going to show you the way that I did it, and it worked. So I took my 1 trial, I took my second trial, and you'll see what it's asking for. I don't want to give too much specifics on this, but it'll ask you for certain values and things, and you'll have to do the percent trial. So it's going to tell you what it wants for the percent error. I took my first trial, I took my second trial, I subtracted them. These are absolute values, so I'm not worried about negatives. And then I took my average, and that's how I determined my percent error. And I left it as a positive value, even if I had negative values for this. But you should still use the negative values till the very end, because adding something and subtracting something and removing a negative sign could mess you up. Okay, calculations for alcohol fuel. All of you are going to get different fuels, and there's a whole bunch of them on there. This is the one that I was given. And the nice thing about it is they don't give you the molar mass. So if once you get your fuel, you're going to have to look up the molar mass. There's no listing for it. So this is all my information that I was given. I have my initial and final, so I have my mass, and I have my temperature difference. And I'm going to use the value from the first part. And these are the equations I'm going to use for this. So the first thing is I want to know my heat flow. So I'm going to take the 9.848 kilojoules per Celsius that I took from the first part of this, and my temperature difference from this lab. And I'm going to multiply them because the C's will cancel out. My heat flow is 1 unit, and I have it, and it's a negative number. This is an exothermic reaction. The next part, I'm going to determine the moles. The moles, you have to take the mass and get the moles. It's that simple. Don't let it overwhelm you. You guys have done this before. So I take my 1.34 grams, I take the molar mass I had to look up, and I now have my moles. 3 is kilojoules per mole. So this should also give you an idea of what you need to plug in. Look at the units. If you are lost, the units will help you. So I'm going to take my value of my kilojoules, which is my negative value, and I'm going to plug it in and divide by 0.152 moles. That's going to give me my delta H, and my units are kilojoules per mole, and I have a value there. I did follow sig fig rules, by the way, and I did get everything correct for that. All right, so here is this portion. So this technically, if you follow sig fig rules, it would be 3 sig figs. So 3,102, 0.0. If you would have left it out, I would have cut this off. I would have only left it with this. So 3120. Okay, so QG. 2 ways to calculate it. PDF does both. I'm going to show you how I did it. Q reaction, mass burned. I take the mass that I subtracted and determined with my kilojoules, and I now have my negative 35.73 kilojoules per gram. So that's how I determined that one. And you're going to do 2 trials of this. They don't, LabFlow sometimes makes things more complicated than they need to be. So take your time with it. follow the PDF shows you. I'm showing you how to do it. Follow your instinct on what you think is right. Follow the sig fig rules. Follow the negatives. All of this stuff is very overwhelming, so take your time with it and make sure you thoroughly read, even though it is a lot of reading. This chapter is 2 weeks, and this is our second week, so by now you should have already read most of it. So this should have some familiarity, I can't say it, to you. I strongly suggest you read chapter 6 before you do this lab, at least the last section, because you're going to have a question at the end on the very last section of this chapter. So when balancing, you have to keep everything as 1 gram and 1 mole. That means that you might have fractions in between the balanced reaction, except for the fuel that you're using. That has to stay as 1. Don't forget to upload your calculations. I will check them. Thermochemistry is not easy, and you have to stay up on top of it to make sure you follow it. Negatives really mess people up. Take your time, write things out clearly so you don't make small mistakes. Read the PDF thoroughly. Yes, it's a lot of pages, but the more you read it, the more you understand, the easier this lab will be. Don't forget negative signs. I did the first time I did this, and I got things wrong that were not wrong. They were just wrong in the sense I forgot the negative sign, but LabFlow doesn't tell you that. I didn't enter any units on LabFlow, and it was still counted as correct. If you get confused with the question, look at the units. Units will help guide you into what you need to do. You'll have to look up the molar masses. There's a safety portion in the PDF, something that you answered in the very first quiz of this semester. So you may have to refer back to some of the safety stuff. So if you want to watch that video before you start that quiz, you may want to do that, because there's some safety questions about fire and so forth. And last section, you're going to have to do the standard state of heat of formation values to answer the last couple questions in this. If you haven't done chapter 6, you're going to be completely lost when you get to the end of this section of this lab. And you have 2 attempts, which is great. So you can, if you think that maybe you forgot a negative sign, you can add it, and hopefully you have the correct